Hi, my name is Alexander Koenig, and I'm recording this talk that I've given at the Safe AI in All Domains workshop at the CVPR conference in Vancouver this year. Our paper is called Uncovering the Inner Workings of STEGO for Safe Unsupervised Semantic Segmentation. The paper is co-authored by Max Schambach and Johannes Otterbach, who have collaborated with me on this project at Merantix Momentum, which is a Berlin-based startup working in machine learning consulting and research. A common problem in machine learning is the lack of labeled training data. However, unlabeled data is often readily available. Self-supervised learning has recently demonstrated impressive results on such unlabeled datasets. For example, the STEGO algorithm below is an architecture and training strategy for unsupervised semantic segmentation presented at ICLR last year. In order to apply algorithms like STEGO safely in real-world settings, it's crucial to understand their working mechanisms. For STEGO, we identified some reproducibility issues and missing benchmarks that assess the contributions of this approach in more detail. Here's a brief recap on how the STEGO algorithm works. STEGO consists of two parts, the DINO backbone and a clustering algorithm. First, the algorithm extracts dense and highly expressive features using the pre-trained DINO Vision Transformer in yellow. Consequently, a segmentation head S projects the DINO features into a lower dimensional space. The segmentation head is trained contrastively and distills the DINO feature correspondences. Afterwards, STEGO performs unsupervised k-means clustering on the projected features. Finally, the Hungarian matching algorithm maps the detected clusters to human interpretable labels. In our first experiment, we conduct a reproducibility study. The original STEGO paper reports the unsupervised REU performance in blue. It also evaluates the quality of the segmentation head features using a supervised linear probe in red. Furthermore, the paper also states the performance of the vanilla DINO backbone on both tasks. First, we find that using the pre-trained models of STEGO, we can reproduce the STEGO performance for both evaluation styles, highlighting the correctness of our evaluation protocol. Furthermore, our results demonstrate a considerably stronger performance of the vanilla DINO backbone on the unsupervised clustering task, and especially the supervised linear probing task than noted in the STEGO paper. In our second part of the study, we set out to identify the factor that makes STEGO perform better than DINO in the unsupervised evaluation. First, we benchmark STEGO's linear probe performance across different embedding dimensions of STEGO segmentation head, which is noted on the graph's x-axis. We identify that STEGO, in orange, can robustly downproject the Vision Transformer's embedding dimension by a factor of 10 with little loss in supervised performance. Therefore, we conclude that STEGO is an efficient dimensionality reduction technique. It is well known that the k-means algorithm converges better in fewer dimensions due to the curse of dimensionality. Hence, downprojecting the feature dimension before applying k-means will positively impact the unsupervised performance. In this last study, we find that besides STEGO's dimensionality reduction, there is another key factor benefiting STEGO's unsupervised performance. The graph also shows a boost in unsupervised performance when the segmentation head retains the Vision Transformer dimension, in this case 768. This is likely due to the contrastive training of the segmentation head, which transforms the bit features to form more distinct clusters on which k-means converges better. If this presentation has piqued your interest and you want to find out more about safe unsupervised semantic segmentation, please read the paper, and if you have any questions, please reach out and shoot me an email. Thank you so much for your attention.